Hello and welcome to this section of the Circuit Analysis Tutor. Here in this section we're going to continue talking about voltage dividers, and we're going to talk about this circuit here, which I think is an interesting circuit. The first time I saw a circuit similar to this, it kind of took me back for a second. What you have is a voltage source. You have resistors that are known everywhere. This is 2 kilo ohms, 6 kilo ohms, 9 kilo ohms, 3 kilo ohms, right? And what you're asked to find is the voltage across this empty air here, basically, from this terminal between these two resistors to this terminal between these two resistors. And that knocked my socks off the first time I saw it, because up until now, you've always been asked to calculate what's the voltage across this resistor, what's the voltage across that resistor, what's the voltage across this current source, and so on and so on. You're always measuring voltages across physical items. Here, you're asked to measure a voltage across thin air, and so it doesn't really make a lot of sense. But you have to realize that it's perfectly legal to find a voltage drop between any 2 points in space at all. I mean, even if there's no circuit there at all, if you go back to physics and you go in deep space near a star or something, there's a potential here and there's a potential here, and you subtract the value. What's the potential here? What's the potential here? Subtract them, you get the potential difference between 2 points. Here, you obviously have voltages everywhere. There is a voltage drop across each one of these components, but if you take a voltmeter and you actually hook it up between these 2 points, there's a potential difference between these 2 points as well. And all it means is the voltage between here, there's no current going through here. There's no path to conduct any current. That's why it looks weird. But what it means is that between these two resistors on this side has a certain value of voltage. Between these two resistors on the other side has a certain value of voltage. And when I hook a meter up between them, I'm just subtracting the values. It's the potential difference between those 2 points. So our strategy here is going to be to figure out, if you think about it, and I'll blow your mind here in a minute with something else, if I can calculate the voltage drop across this resistor, which I think I can do, and if I can calculate the voltage drop across that resistor, which I also think I can do, then I should be able to write a Kirchhoff voltage loop that goes from here, here, across that voltage drop, and then back up, making a loop. Now, that should blow your mind a little bit, because I never told you you can do that. The truth of the matter is you almost never want to do that. It's just these specially constructed problems where you would ever care what the voltage is across these two random points in the circuit with no electrical path between them. Typically, you're always concerned with what's going on with your circuit components. But Kirchhoff voltage laws really comes from physics, really. It's talking about the potential that you gain and lose as you go around any closed path in space, back to your starting point, really. So if you go back to your physics, right, where you talk about, and I do have a physics series as well which talks about this, which talks about potential, just in general, electrical potential, right? Not even talking about circuits, just in talking about electricity and magnetism. Then the voltage that we call it, electric potential is really what we call it, between 2 points is just simply subtracting the value of those two potentials at those two different points. But you can also go in a closed path in space, and if you get back to where you started from, even if you didn't travel on a circuit path or whatever, you should get back to the same voltage spot, the same potential spot that you started from. And that's another way to restate Kirchhoff voltage law. It's just that we always apply Kirchhoff voltage law along circuit traces, because that's generally what we care about. We care about finding these currents everywhere. But it totally applies. If I start in this corner and I go add up all the voltage drops and all the voltage gains to get back to this corner, by physics, it has to be valid. So don't get too freaked out about that. It's a little bit weird, but if you're ever given a question where you have to find the voltage across empty space, go ahead and do a Kirchhoff voltage loop. It's totally fine to do. Just do it in the same way that we've always done. We can't do it straight away because we don't know what any of these other voltage drops are. So that's where we're going to tie in the voltage divider. Notice what we have here. 18 volts connected across these two resistors. This same 18 volts is also connected across these two resistors. So these two guys are really in parallel. This 18 volts is across here. This 18 volts is also across here. So I can do two voltage dividers, really. So if I want to find the voltage across the 2K resistor, then it's going to basically be 18 volts times the 2K resistor, 2 times 10 to the 3, divided by the sum of 2 times 10 to the 3, plus 6 times 10 to the 3. What I'm doing is I'm using a voltage divider here. I'm tapping, I want to find the voltage across here, so this is on top, the sum is on the bottom, right? And when you do this, you'll get 18 times 0.25 so you get 4.5 volts. So what this means is that the current is going this way, the current is going down, so that should be plus minus 4.5 volts across this guy. Now, if I want to find the voltage across the 9K resistance, this guy up here, I do the same thing. 18 times. I have up here, I'm tapping off the 9K resistor, so 9 times 10 to the 3 over 9 times 10 to the 3 plus 3 times 10 to the 3. So again, it's what I'm tapping off of goes on top, the sum of the two guys in the same leg goes on the bottom. And so what you'll have is 18, and you'll have 0.75. And so when you multiply these guys together, you get 13.5 volts. 13.5 volts. But don't forget the polarities here, right? I know the current is coming out like this because that's the source direction, right? So when it gets here, the current has to be coming down. When the current has to be coming down, then they rejoin over here. So let's write a KVL, and this is going to be our loop. We're going to go down this resistor, across empty space, but we know there's a potential there. Okay? Between any 2 points, there's always a potential difference. We're going to call it V sub x. And then we're going to go through this resistor back to where we started, and that's a loop. So what we're going to have over here, remember, current's going this way, so the voltage drop here has got to be plus to minus. So when we go along our path, it's going to be positive 13.5, because that's the voltage across this resistor, 13.5 volts. Now when I jump across the empty air, I'm just going to carry that over as a Vx, an unknown variable, and I'm going from plus to minus, so it's going to be plus Vx. Now when I go back through the 2K resistor, I'm going against the current flow. Current's coming down here by the direction I have here. So it's going to be plus minus voltage, and I'm going opposite that. So I need to subtract the voltage across the 2K resistor, which I've calculated as 4.5 volts. Let me take off the V. And then you get equal to 0. So what you have is Vx plus, when you take this and subtract this, you get 9. And that's equal to 0. So Vx is equal to negative 9 volts. And this is the answer to the problem. Now, don't get freaked out because you got a negative here. It just means that this was given in the problem. You've got a label across this, right? You've got a label that says plus to minus, but in fact, the way the actual circuit's constructed, the voltage is flipped around. This is actually the high side, this is actually the low side. It's the same thing we've been talking about in all the other problems. If you get negative, it just means opposite. So there's two things that I really want to drive home in this problem. First one is, since you have this 18 volts across two different voltage dividers, you can certainly apply voltage divider law to two separate legs to get whatever it is you need to get. We calculate the voltage drop here by using this. We calculate the voltage drop across here by using this. It's exactly the same as we did in the last problem. Now, the second major thing is that you really can do Kirchhoff voltage law across any closed path that you want in a circuit. It's just that typically we stick to the circuit traces because that's what we're interested in. We're interested in finding voltages across things, currents in resistors and things like that. This case, it's a little bit tricky. I want you to find the voltage between two empty points in space, which is totally fine to do. You could get a meter up and measure this value, which is going to be 9 volts, or negative 9 volts there. And so you can do that. You just have to keep the directions right. So when we go down here, we're doing a voltage drop, so that's positive. This is another voltage drop, so that's positive. This is a voltage rise because current's going this way, so that's negative. And we solve for Vx, we get negative 9. This just means that if we really wanted to label it right, we could switch it around and say that's 9 volts going the other way. That's not what we were asked to do. You would circle negative 9 as your answer because your label, which was given to you, is labeled in that fashion. So you have to stick to that labeling, right? So that does it for voltage divider. It's not hard. Mathematically, it's some addition and some, division and some addition. Very, very simple, but knowing how to apply it and knowing what it means, that it splits that voltage up proportionally based on the resistors you have, internalizing that's really important because you look at larger circuits, you'll start to see, oh, there's a voltage divider going on there. Oh, this circuit is just simply tapping off a voltage that it needs to operate. So you see a very large circuit, you start to look at it in chunks. You'll say, well, this is the power supply part of the circuit. Here's my power source. This is the part where I'm doing the radio antenna, or whatever it is I'm building, you know, my computer or whatever it is I'm building. And then the connection between these two parts of the circuit is just getting the proper voltage to that part. So you know, when you start, you might look at the whole thing and say, this is enormous, this is very complicated. But you begin to start looking compartmentally at different parts of the circuit and say, okay, this guy's functions to do the power supply, this guy's functions to do this, it's connected here, this function is to do this, and so on. And that's how, you know, a lot of circuits really are constructed, and radios and cameras and TVs and things like that. So make sure you know how to work this problem, work it yourself, and follow me on to the next section where we're going to begin to talk about current divider circuits.